Hey guys, so I've been doing a little bit of tuning on this motor. I'm gonna show a demo here how it completely eliminates Lenz's law. I've only had the time to work on this motor. I've tried a couple of quick tests on the other motors that I have, and I haven't been able to get it to do it with the other motors. The geometry of the magnets and the coil size and spacing is really important to get this effect. And also the timing circuit on the driver coil is really important to be able to make it work. So right now I'm not collecting any of the back EMF. Here's the negative right here. And here's the positive. They're not hooked up on the output, which is right here. This is hooked to that coil back there, collect where that bridge rectifier is on. It's just on the AC. It's just a coil that's not doing anything. It's just registering the frequency. Here's the I'll get a pen here to point. So here's the input. This is the current. See how it lags behind? It's set on the 1 millivolt equals 10 milliamps. So, and that's on the number 1 scale. So here on the VB on the bottom, you can see 103 or so millivolts. So that means when it's down here, there's just over an amp pulse going in. But you can see here on this, it's registering about 55 milliamps or so. So that's the current on the bottom. This is the input voltage going into the coil. This is the back spike, the flyback. And then it rings for a bit. And it's off and turns on again. This is the PWM signal for one magnet. As you can see here, as I zoom out, you can see the sine wave where it's off on this one, and it fires again on this side. So it's off 50% of the time, while the Hall effect is away from the magnet, like not turning the drive circuit on for 50% of the time. That's off for more than 50% of the time because of the PWM signal. I'm zooming in here on the PWM signal. You can see there's the back spike. That's the on time. Here's the current. And you can see how it fights itself right here. Because there's current still going in this way. This back EMF is fighting this right here. Ideally, this should be over here. And this would be here. Then it would make the motor go faster. So here's the frequency. It's running on about 13.1 or 2 volts or so in that area. I haven't even checked with the voltages, but it's somewhere around there. 13.1 on this gauge. Alright, so now let me show you a few different things here. First, I'll start by collecting the back EMF and the light bulbs, and then we'll see what it does with the frequency, and we'll check out what the scope says. So I'll hook that up now. Negative goes there, and then this one goes here. Now the lights are coming on. See the frequency. It should speed up a little bit. I don't expect it to speed up very much, but it'll speed up. Now you can see that the current here isn't affecting the motor anymore. Not as much anyway, there's still a little bit of a fight there. Current has dropped a little bit, not much. Just a hair less. Get a better reading on a different time scale. It's went down just a bit. And the RPMs have went up a little bit. It's still increasing a bit. The lights are on. So now I'll take this off, take the negative off of here. And I'll send that back spike right back into the motor. You can hear the tone change in the motor. It's speeding up drastically. And eventually the current will go right back to where it was or even lower. But now look it on the scope. There is no more back spike and there's nothing fighting it at all with the current. There's nothing below this coming down to fight this current anymore. It all gets harvested and used into the next pulse. That's why the motor's speeding up. And it doesn't have to fight itself anymore. You can see it has dropped. The input current has went down. You can see it on this reading right here too. It's dropping a bit, kind of bouncing around just because of the scope where it's getting its readings, but you can see overall it's lower than what it was. It's still speeding up. I completely eliminated Lenz's law with this driver circuit. It's the driver circuit that's doing it. equaled out there. I forget what it was before. I think it was 45 hertz, I think. And drop the current level. The motor sped up. And it is under load, obviously. Here's a fan here. Yeah, just take, like, it's really important to have the magnet spaced properly. They are north-south. It fires 50% of the time. Means on 50% of the magnets. You can see here, they are spaced perfectly for the coil. Your coils ideally want to be rectangle. And you want your magnet to be able to fit easily on the center of the coil. You can see over there on that side, it's the same coil, but they fit perfectly. And like when that one's there, the next magnet is ready to fire. It's really important to have your spacing right. Nothing. Let me see what it does when I'm not even moving. See, there's still no back spike when I'm feeding it back. Your coils will never ever get hot like this either. Your whole circuit will run cold. Well, cool. You're still putting current through it, so it's going to heat up a bit. But see, it's above 46 here now. Take that off. Not collecting any back spike anymore. There's a big back spike there. They're 20-volt intervals, so we got 60 volts or so. 63 it says here. The motor will try to sustain itself there, but it's slowing down. It'll go down to wherever it was before at 45 hertz or so. That's because you can see the back spike interacts with the current. Put it back here to collect it, and it goes right back through the driver circuit. Motor speeds up. And the current will eventually drop. So that gain in speed is extra power you can harvest. Either mechanically or electrically, whatever. But just wanted to share that. Thanks, guys.